Okay, welcome back everybody. We are looking at Theorem 6.1 on page 130 of the workbook here. And we're going to kind of talk through this theorem and then prove a couple of parts of it. And this is another big long list of properties that inner product spaces have to have. Okay, and as you read down this list, I'd ask you to notice that a lot of these properties sound similar to the defining properties of the inner product space. For example, statement A here is basically saying that in an inner product space we have linearity in the second coordinate. Okay, in the definition of the inner product we had linearity in the first coordinate. We're just proving a generalization of that. Okay, B was also similar to the second property in the definition. Okay, it's basically saying we have conjugate linearity in the second coordinate. So if we take the inner product of x with a constant multiple of the second vector, we can pull the constant out as a complex conjugate. Okay, maybe just reading the third property together just tells us that the inner product of any vector with the zero vector is 0. And I'll let you read properties D and E on your own. Okay, and here's what we're going to do. We are just going to prove properties D and E. And I'll make the remark that properties A through C are either exercises or they're proved in our textbook. Okay, and the remark that I'll make before we prove D and E is that we're going to assume that somebody has proven A, B, and C for us. Okay, so we're going to feel free to use those three results when we prove D and E. All right, so let's start with some arbitrary vectors, x, y, and z, and a scalar. All right, so property D, notice that that's an if and only if statement. We would like to prove that the inner product of a vector with itself is the scalar 0 if and only if the vector is the 0 vector. Okay, so since that's an if and only if statement that we're trying to prove, we need to go in both directions. Let's start with the left to right implication. It turns out that that implication is easier to prove by contrapositive. So instead of assuming that the inner product of x with itself is 0, we're going to assume the opposite of the then part. Okay, assume that x is not the 0 vector. Okay, well, if that's the case, then we know from part D in the definition of the inner product that the inner product of x with itself is greater than 0. So there's our starting point. Okay, and if that inner product is greater than 0, it's certainly not equal to 0. Okay, so we've actually proven the forward implication. Okay, we started by assuming that x was not 0 and proved that this condition, that xx is equal to the inner product of x with itself is 0, is also not true. Okay, so going in the reverse direction, this direction of the proof will do directly. Okay, so here we'll start by assuming that x is the 0 vector. Okay, we'll take the inner product of it with itself. Okay, and I claim that that inner product is the scalar 0 by using part C. Okay, why? Do you see why that's the case? Okay, part C tells us that the inner product of any vector with the 0 vector is 0. So what we did is we basically made the observation we can choose x to be 0 and we get a true statement from C. That's kind of all there is to proving the reverse direction of this statement. Okay, so I think we've proven part D. Okay, let's move on to E here. All right, and this is going to be kind of a sneaky method of proof that we use here. Okay, so we'll go through the argument and then maybe say a word about the strategy at the end. Okay, so we'd like to prove that if the inner product of x and y is equal to the inner product of x and z for all x and v, that's very important, then it turns out that these two vectors, y and z, have to be the same. That's what we're trying to prove. All right, so let's suppose the if part of this, that the inner product of x with y is equal to the inner product of x with z. Okay, and again, we're making that assumption for all x and v. That's a very important hypothesis. And what we're going to do is we're going to look at the inner product of x with y minus z. Okay, remember what we're trying to show here is that y is equal to z, so our strategy is going to be to try to show that y minus z is 0. That's equivalent to saying that y is equal to z. Okay, so first observation, if we use part A up here, we can split that up using linearity into the inner product of x with y plus the inner product of x with negative z. Okay, then that's equal to this. Do you see where we got that statement? We took the minus 1 that was in front of the z and pulled it out as a complex conjugate. That's really using part B up here. Okay, but what happens when you take the complex conjugate of a real number like minus 1? Well, it doesn't change. It stays the same. There's no imaginary part. So the conjugate of negative 1 is just negative 1. So we've got the inner product of x with y minus the inner product of x with z. But what did we assume at the beginning of this argument? We assumed that those two inner products are equal, which means that we're looking at 0 down here. And I emphasize again that we're getting 0 for all x and v. That was part of our starting assumption. Okay, so here comes the sneaky step. If this is really a true statement for all x and v, then we are free to choose any vector we like for the x. And so what we're going to do is to choose x to be y minus z. If we do that, here's what we have. Okay, so we'll go back, substitute y minus z in for that x, and we're looking at the inner product of y minus z with itself, and coming to the same conclusion that we have to get 0 out of that. So the inner product of y minus z with itself is equal to 0, but take a look back at what we proved in part D. D said that if you take the inner product of a vector with itself and you get 0, then that vector has to be the 0 vector, so we have just proven that y minus z is 0. Okay, and if y minus z is the 0 vector, then that means that y is equal to z, and that's what we wanted to prove. Excuse me, y equals z. Okay, so very interesting strategy that we did there, very indirect method. We wanted to prove that y is equal to z, so we proved that y minus z is equal to 0, and we did it in a very indirect way by proving that the inner product of the vector with itself is equal to 0. That gives you a little bit of an illustration of some of the techniques that you use in inner product spaces.